time to start.
Okay.
Yeah, perfect.
Thank you.
Welcome.
Well, my talk will be about perturbative expansion of thermodynamical effect of Hamiltonian. And this is the outline of my talk. Well, I will speak about some basic definitions, what effective Gibbs state and what I'm generally speaking about. And then I will formulate the main results and move to some, how it is related to some effective thermodynamics. And then I consider some example and come to the conclusions. Well, what is this, the setup of the problem which I consider? I consider very specific observables, and namely time-dependent observables, and long time scale. Namely, I consider a Hamiltonian of the very usual, I think, form some free parts H0 and some small coupling lambda times interaction Hamiltonian. And I consider very specific observables which are time dependent in the following way. They are usually we see something like that, but with inverse signs in the interaction picture. But here we have some directly time-dependent observables which depends on time in such a way that in the interaction picture they became time independent. So we have why this setup is natural, because usually when we consider some external classical electromagnetical field interacting with n-level atom in resonance situation, we will see something like that. We are finding such an observables. Usually it's some dipole operators in classical electromagnetic field, which are time dependent in such a way that in the rotating picture or in interaction picture, they would be time independent. So in this sense, these observables are time dependent in resonance with free Hamiltonian, and it is usual situation for the spectroscopic setups. And we are interested in the long time scales, meaning that we have such time scale that omega times this time scale is much larger than 1 for all non-zero Bohr frequencies of H0. Bohr frequencies is just transition frequencies of the free Hamiltonian, is just all possible differences between eigenvalues of H0. And we assume, of course, that A is time independent. So this A in the interaction picture, that is time independent just for simplicity. It is also possible to add here the time dependence, but some slow time dependence, which is for which this condition does not hold. But it's just more calculations, but nothing important will occur here. So we just think that we have the following form, just for simplicity. And I will consider actually the thermodynamics, the equilibrium of thermodynamics, and for such observables. And the equilibrium of thermodynamics is described by canonical Gibbs states. It is just usual canonical Gibbs state, but for on these long time scales, I assume that I observe only long time averages. So long time in the sense I said already. So this leads that we actually do not observe the canonical Gibbs states in all details, but we have some effective Gibbs states obtained by applying to these Gibbs states a projector of averaging with respect to free evolution. It could be written as this average, or it's this sum in terms of eigenprojectors of the free Hamiltonians. In this situation, it's more clear that it is averaging, and in this representation is more clear that it is projector, for example, and or for example that it is completely positive projector, because these pi's are actually they of course self-adjoint as a projector, eigenprojectors of the self-adjoint Hamiltonian, so they're nothing else but Krauss representation of this map. So sometimes it's better to use this representation as sometimes the other one. And I consider actually not just the Gibbs states, but effective Hamiltonian. And effective Hamiltonian is just some kind of resummation of the, well, I will calculate it perturbatively, is some resummation of this the corresponding series. Namely, I will try to represent these effective Gibbs states also in a Gibbs-like form with some effective Hamiltonian. Possibly it could be temperature dependent. I have not written it explicitly, but in usual situation it would be. And well, the partition function would be the same. It would have the same formula both in initial Hamiltonian and in the final effective Hamiltonian. Well, and the main result is actually the perturbative calculation of such an object. So it's possible to obtain accumulant-like expansion, because in any case, when we are trying to estimate not some asymptotic expansion, some asymptotic series, not directly, but in exponential form as exponential of some asymptotic series, we have something like cumulants, more or less. So this is explicit formulas. For this series, these kappa n are some kind of non-commutative cumulants here, and they are defined by expansion of perturbative expansion of the this effective Gibbs state. This is just usual terms of the Dyson series, nothing else. Well, this is explicit formula is, I think, main result, and but to make it more explicit, because it is not very good to calculate something just by this formula. Just as usually done when we derive a quantum master equation, it is more easy and more better for explicit calculations to represent the interaction Hamiltonian as a sum of eigen operators for the super operator of commutator with H0. So this H0 commutating with something, it is a super operator. It maps operators to operators, and this means nothing else that this d omega are eigen operators of this super operator, and we just represents interaction Hamiltonian as a sum of such eigen operators. This leads to the following formula for this construction when this projector acts on the products of this hi dependent on the beta in such a way, and it is easy to see that all these mk are fully defined by these products. So it is possible to use it, and then the explicit formula for mk of beta are the following one. Here we have the eigen operators, and here we have the some coefficients. Here an explicit formula for these coefficients. I have already presented some of these results on previous conference, but I think most of them know this explicit formula for any k. So I just have written only 0 first terms before, and here's general result. And sometimes it's possible to have here a 0 denominators. In this situation, this formula should be understood as a limit. Now let us consider just 0 first terms. The 0 order and first order terms are nothing else but rotating wave approximation, and it is the reason why I call it effective Hamiltonian, because effective Hamiltonian usually it is called something when we have some corrections to rotating wave approximation in many different setups, usually in some dynamical setups, but here we have some equilibrium setup. And the second order term is first non-trivial temperature dependent correction. So the first 0 and first terms of the perturbations theory are temperature independent, and here's first temperature dependent correction. Let us mark that it is non-positive as an operator. So it is easy to see from the fact that here we have the dagger, and here some positive function. And why I remark it, because I will show that it is directly connected to some thermodynamical properties. Namely, let us consider, well, as usually thermodynamics is described by free energy. We know how to calculate, and free energy in statistical physics is defined by partition functions. So we know the formula for partition function here, so it's possible to define the free energy, entropy, and so internal energy here, and so on. But what is about usual statistical properties, statistical formula for entropy and initial and the internal energy. For exact Gibbs states, it's just usual thermodynamics. We have this formula, and for effective Gibbs states, we can use also this formula, but then we define something else which is different from these exact results. And what is it? It is always possible to think about it as some change of this change of the entropy, as some change of our knowledge, some information loss due to the fact that in this setup we have not access to all the exact Gibbs state, but we have restricted experimental setup in this situation. So this is some kind of information loss. I took the minus sign here to make it always positive function. It is possible to prove that it is always positive. Here is an explicit formula for this change of the entropy due to this information loss, and the same formula to change, actually not change, but difference between actual internal energy and some effective internal energy that we think about the system has based on our restricted experimental setup. But the free energy would be the same by both formula. It is possible to show that it is always non-negative. As I said, it is just general non-perturbative result. But if we move now to the perturbation theory, we will have a direct connection to this second order term. If it is non-zero, it's in generic situation, exactly this second order term of the perturbation theory defines this entropy change or information loss. And its positivity is directly related to the positivity of this information loss. And let us consider an example. It is just two interacting two-level system. It is possible to consider the off-resonance situation when the frequencies of one two-level system and second two-level system are essentially different. Then we will obtain the following effective off-resonance Hamiltonian, where the function f of x is exactly defined by terms like this. It's not exactly this, but some derivative of it. So this is just explicit result. So in the zero order we have just free Hamiltonian, and here we have second order correction. But one would say, well, where the rotating wave approximation here, but for off-resonance situation, actually the rotating wave approximation gives us just free Hamiltonian, and some non-trivial terms from the interaction occurs only when the frequencies are very close to each other. And well, it is the last slide about off-resonance situation is just direct computation of this information loss, just explicit formula. And for resonance situation, we should consider the frequencies are exactly the same, or it's also possible to consider the situation when the frequencies not exactly the same, but their differences are of order lambda in our coupling constant. So it is possible. Then the sorry, here's a mistake. It should be resonance now situation. For the resonance situation, we will have as a rotating wave approximation this Hamiltonian. So we have both terms from the free Hamiltonian and from the interaction, but the rotating in right way when terms when we have minus and plus here, but not we have no terms plus sigma plus here, or something like that. That's like in usual rotating wave approximation, and some second order corrections. These in leading order, the information loss has the following form. It is also possible to think what is do these results coincide when the frequencies are equal, and the answer is not. Thus, off-resonance averaging leads to larger information loss even in the resonance limit than just resonance averaging. So it's actually possibly it's obvious, but nevertheless. And I will turn to the conclusions. We have considered the perturbation theory for such an effective Hamiltonian, and what is important for further generalization. It is important that we just taken some projector, some projection superoperator, and consider some effective Hamiltonian for such an effective some such projector. Why I interested in this story? Because actually in the theory of strong coupling equilibrium quantum systems, strong coupling means we actually that the coupling is important. It is not possible to have just product states of system and heat bath. And this means strong coupling. It not necessarily means that it is non-perturbative. It's actually usually perturbative. Then the main object is so-called mean force Hamiltonian. Mean force Hamiltonian, and it's possible obtain it in exactly the same setup, but with different projector. Actually, the projector should be used here is just usual standard projector, which is used to derive.
Sorry for interruption, Alexander. You have 4 minutes to finish. Okay.
Okay.
Yeah,
actually conclusions. The main object of this strong coupling equilibrium quantum thermodynamics is mean force Hamiltonian, and it's could be obtained exactly in this setup just by another projector, which is usually used to derive standard quantum master equations. And so it's taking different projectors, one obtains different effective quantum equilibrium quantum thermodynamics. So it is possible to have one effective quantum thermodynamics per each choice of the projector. So this theory suggests very wide generalizations of the equilibrium quantum thermodynamics. And I think this is the main philosophical results of this work. And the details could be found on this archive preprint. So thank you for your attention.
Thanks.